So typically there are two types of searching, linear search and binary search. And there are various types of sorting, but I'm not going to cover everything in this class. Probably you will see a lot of sorting things in 2420 class. I'll be overviewing some of the sorting technique. And then what you need to do for this week is like you need to know why it is different from our regular searching and sorting, like Python built-in function, like sort and sorted. What type of sorting is using in Python basically. The exam I already have told you. And then the final exam, you need to understand the project description before going to the next week's. Okay. Okay. Searching. What is mean by the searching? Searching
Searching a list for a value.
Searching a list for a value or searching a value from a list. Okay. So finding something, right? Searching. So there are various types of searching, various ways to search. So whatever data structure we have learned so far, string, list, tuple, dictionary, sets, what else? That's all, right? So these are the data structure. So data structure is like you're storing data as a collection. From those collection, we need to find an item. For example, it's better to have board and projector. So for example, this is my list 1, 2, 3, 4, 5, 6. Okay, this is a list. Maybe I would like to search for. How I can search? If you are given a pile of files and you're asking like, find out that particular file, how do you find it? For example, there's like case file. There is a case number on top of the folder. There are like 10 case files. I'm asking you, can you find the case file number 10? How do you find it? Start working with the top, right? Is it the case number 10? If it is, then you find it. If it is not, go to the next one. Is it 10? No, it is not. Maybe it is. So you'll keep searching until you find the exact match. What if you don't find it? There's like, so we don't have the case file number 10. But in Python, it returns a -1. If it finds, it returns the file itself or the index. If it doesn't find it, then it will return the -1. So as we know, the index starting from 0, if you return -1, that means you don't find it. It is not there. So the same way, it's a list. Maybe I like to find the 4. I can search with, like I will match 4 with 1. Is it 4? No, it is not. I will move forward. Is it 4? No, it is not. I will move forward. Is it 4? No, it is not. Then is it 4? Yes, it is. I don't need to search for the rest of the numbers just because I find it. This type of searching is called like linear searching. So we're searching from beginning to the end. When we find it, we return from there. Linearly, we're searching. So linear means like since it is a list, a collection, we're starting from the 0th index. We're searching all the way to the end of the list. Linearly, we're not jumping from 1 to the 2nd to the 5th. We're searching one at a time, or we cannot going through 0 to 6, then 6 to 2, 2 to 5, 5 to 3, 3 to 4, not like that. We have to search linearly, right? So in a linear search, let me go through those things first. This is an example, searching a student ID from a database, or sorting is not covered today, so I'll be discussing sorting next class. As I told you, there are two types of searching, linear search and binary search. And these are the learning outcomes of this week. You'll understand the basic concept of searching and sorting, describe the linear search and binary search algorithm, implement searching algorithm in Python. Then we'll explain and apply bubble sort to organize the data, compare the sorting methods, and Python built-in sort function for the sorting purposes. So for the searching, what means search algorithms serve a critical role in computational system, enabling the retrieval of data from structure, just like trees. Trees, we haven't covered the trees here. Trees is the part of another data structure that will be covered in 2420. Database is nothing but storing data. What we have done here, like file, in a file we have stored the data. So we can say like files are a sort of database, but not exactly. In a real-world computational environment, search mechanism underpin a wide variety of use cases. For example, like locating entries in digital address book, retrieval bibliographic metadata in digital libraries, accessing keyed entries in hash map or relational database. What is a hash map? Have you heard this term? Hash map? What it is?
The map the locations in the memory.
Map the location in the memory. Yes. What else? What exactly the hash map here?
Of the hashable item.
Is that?
Of the hashable items.
Of the hashable items. So what hashable item we have used? You're very close. The dictionary, right?
Yeah.
The hash map. So we hashed the key and then we map the value in the dictionary, right? So hash map is nothing but the dictionary. So yeah, entries in the dictionary or the relational database. We're not worrying about the relational database here. So for example, this is a list. If you want to find 30, whether the 30 exists in this list, how do you do that? In a linear search, start from the first element, compare that element with the targeted value. What our target value? Our target value is 30. We start from here, compare the element with the target value. If it matches, we return the position. If it is not, move to the next position. Continue until the element is found or the list end, either one. So if it finds, we're returning from there, or we need to go till the end of the list. So for this particular case, if we'd like to search 15 from this list, we'll start from here, 10. We compare 10 with 15, no match. We move forward, 25, it doesn't match. Move forward to 40, it also doesn't match. Then when we find 15, 15 is equal to 15, so it matches. So we return from here. We don't need to move to the last element of this list just because we found it. So if we write a code here, so here is the linear search algorithm. I'm not sure how tiny it is from the last row. Is it too tiny?
I have good vision.
Okay. I have to make it a little bit bigger. Just to be. Okay. So here's the linear search algorithm or my function. This is the numbers of the list and this is the target. What I'm going to do, I need to iterate throughout the numbers. There are two ways, either index or the item. So here I have iterated through the index using the range function until the length of that particular list. I will check every time whenever this particular number is matched or not. If it matched, I return the index. If so, every time it checks after the loop ends, that means there is no match, then we're returning -1. That means by default, it returns -1. At any point, if it matches, it returns that particular index. This is what we're doing in the find function. If you use the find function, it returns the index. If it doesn't match, then it returns the -1. So we're just writing a list, a data, and this is our target. The result can be either -1 or some value. So what we are checking here, if it is not -1, that means we found that element at particular index. The result is some index. If it is -1, then it prints this one, element not found. But typically the find function returns -1 or some index value. Here we have some customized printable thing. If it doesn't match, then we're returning, instead of -1, we're returning element not found. Okay. Now, what are the characteristics? What are the advantages and disadvantages of linear search? It is simple to implement. As you see here, we're just going through each one item at a time, and we're just checking whether this particular item is equal to that particular value. If it matched, return that one. If it is not, then finally return -1. It is very simple to implement. It works with any unsorted list. So for my case, it is sorted 1, 2, 3, 4, 5, 6. But if it is an unsorted, it also works for here. So for example, like this one, 10, 25, 40, 15, 30, they are unsorted. It also worked with the unsorted one. What is the disadvantages? Slow for the large data set. Why it is slow? For an example, I have a 1 million data, and maybe 1 million minus 1th item is my target one. That means I need to search from the first one all the way to 1 million minus 1. It takes unnecessary time. That's why it is slower for a larger data set. But for a smaller one, it is okay. For 5, 10, 100, I think 1 million is also a smaller data set. But if it is like 1 billion, a trillion, then probably it's a bigger data set. It will take a longer time. Now the question is, how can we make it better? What are the other ways? Is there any way? Yes, there is a way. The way is the binary search. In the binary search, what you need to do, since it is a binary, like 1 or 0, right? So since it is a binary, let's work with this one. So for example, this one, 10, 30, 5, 9, 20, and 50. Okay. So this is a list. I would like to search an item, maybe 20. In a linear search, I need to go all the way from 1 to the last one to find this one. But for the binary search, we're not searching sequentially or linearly. What you'd like to do, we can split it to half. So this is the half part. This is the other half part. We'll check whether this 20 is the first half or the second half. First half or the second half. If it is in the first half, we don't need to worry about the second half. That means we are shrinking the what it says, like search space to half every time. So for example, 20, like we're looking for 20. So 20 is not here. We're not searching this part. We'd like to search the second half. And then again, we need to make it half. 9 and 20, 50. Again, 20 is not in the 9. So we don't need to worry about that part. We need to worry about this part, 20 and 50. Then again, we need to make it half, 20 and 50. So 50, so 20 is not in the 50 area, it is in the 20 area. So we can find it to 20. So you can see here, I have just iterated 3 times. First time, I omitted this one. Second time, I have omitted that one. Third time, I have omitted this one, like only the third search. If it is like a longer list, for example, like for example, like 100 items. So 100 items, I can split to the 50 and 50. We'll check whether the 20 is the first 50 or the second 50. If it is in the first 50, then we can just remove the second 50 from the search space. We can search from the first 50. Then again, we'll split it to half, 25 and 25. We'll again search, like check whether this target is, for example, 20. 20 is in the first 50 or second 50, like first 25th item or second 25th item. If it is the first one, we can just remove that part. We'll search from this 24, like 25, then make it half, 12 and 13. Is it in the first 12 or the second 12 or 13? So maybe in the second part, so we can remove the first one. We'll search for this 13. We'll make it half, 6 and 7. Is it in the first 6 or second 7? Maybe in the second 7. We can remove the first half. Then again, for the 7, we'll make it half, 3 and 4. Maybe in the second 4, like not the first 3, on the second 4 actually. So remove that part. We can make it half, 2 and 2. Is it in the first 2 or the second 2? Maybe the second 2. Remove the first 2. Then for the second 2, we'll check whether the first one or the second one. That means, so how many times? 1, 2, 3, 4, 5, 6. Only 6 search. So instead of 100 search, I'm searching only 6 times. Does that make sense? The basic. But one thing is really important here, that should be sorted. So those items should be sorted if we would like to perform a binary search. Why it is required? If they are not sorted, how can I check whether the 20 is there or not? But if it is sorted, for example, like 5, 9, 10, 20, 30, 50, what I can do, make it half first. I'm going to search 20 or maybe 30, for example. I will check those two parts, 5 and 10. So 10 is the highest number here, right? So 30 is still greater than 10. That means we need to start from here. We can skip this first part. Then for the second part, we can make it half, 20 and 30, 50. Search for this one, 30. So 20 is the highest value of this part. So is it greater than 30 or not? It is less than 30, right? That means it is not in this area. You need to find out in this particular area. Now we can split it 30 and 50. Again, 30, is it greater than 30? It is exactly matched, right? That means I don't need to search anywhere. So I find it. So this is the required thing for a binary search. The list should be sorted. If it is not sorted, we cannot perform a binary search. Okay. So if someone asks you like, here is the list, you're doing some like linear searching. If they ask you, can you make it better? The first condition is like whether the list is or the data structure is sorted. If they're sorted, only you can apply the binary search. Otherwise, you cannot. Now, what is the strategy? The strategy is called like two-pointer approach. Whenever we're working with a binary search, the approach is called like two-pointer approach. I'm writing a bigger list to make it more easier for you, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. I would like to search 4, for example. So the first thing, I'd have to make sure if the list is sorted or not. It is sorted. That means I can perform a binary search here. Now, how can I do that? I have to put some pointer here. I know the first index. This is the first index. And this is the second index, right? What I can do, I can create two pointers. One pointer is called like a left pointer. Another pointer is called like a right pointer. So if I write left plus right divided by 2, I can integer division. So if it is like a 7 divided by 2, it will be 3. So in case of an odd number, this will give you some fractional. So this will not give you a fractional value, it will give you a round value, right? That's why it is like integer division. So how many items are here? 12. So, well, I would like to go through the index, not the number. So what is the index? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So I would like to create a box. I can map here. Okay. So what is the left pointer and the right pointer? I know there should be at least 0 item, some item. So 0 is the first point. And what is the length? Length is the 12, right? So 12 minus 1 is 11. 11 is the last index, but length is 12. So right pointer is length minus 1, right? That is the 11. So 0 plus 11 divided by 2 is what? 11 by 5 is 2 is like 5, right? That means I can make the cut here 0 to 5 and 6 to 11, so like 2 sections. Now I would like to check 4. So as I know, for the first part 0 to 5, 5 is the highest one. If the 4, like if the 5, like my last value is less than 4, that means it should be on the other side. If it is greater than 4, that means it should be in the first half. So what is our midpoint? Our midpoint is 5th. And what is the value? Value is 6. So 6 is greater than 4. That means it should be in this area, right? We don't need to worry about the second half. So we're done for the first iteration. Then we'll jump to the second iteration, right? We'd like to do the same thing for this shrinked list. How can I shrink it? Either I can remove all of the item or just move the right pointer to here. Now my right pointer is here on the next run. Now on the next run, my right pointer is not len minus 1. Right pointer is the mid value. What was our mid value? 5. Our left pointer is still there, 0, and mid value is 5. On the next run, it will be 3 for the mid pointer, right? So we'll make it half to here. This is our mid pointer. It's better to search for a different number. Then I'll find here. So maybe 3. We're looking for 3, not the 4. Okay. So now mid pointer is the index 3 and the value is 4. Or maybe we're looking for 5. Then I can search the other half. So I'm looking for 5, but the mid value is 4. That means the value 5 is in that part, not in this part, right? So you can shrink that left part for the next iteration. But how I can use that next part? The same way, we can move the left pointer to here. So now the left pointer is here, right pointer is there always. The left is mid the value. So mid value was 3. Now it is the left pointer. The left value is 3, right value is 5. So 3 plus 5 divided by 2 is 4, right? Now we'll check 4. This is the mean value. We'll check whether this particular one is greater than or less than 5. I can find the 5 is the exact value. If we find it, we don't need to go further. We can return that particular index. Does that make sense? The two-pointer approach, left and right. Whenever, so every time, starting from the beginning, we'll find the mean value by this way. Then we will check the mean value with our target value. If the mean value is greater than our target value, that means we have to shrink the right pointer to the mid position so that I have the left part only. We are not worrying about the right part. In the other way, if the mid value is less than the target value, that means we don't need to worry about the left part, we need to worry about the right part. We need to move the left pointer to the mid position. That's the strategy. And how long we can iterate this one? As soon as the left pointer or right pointer are not changing their direction. Like at some point, if the, for example, I'm looking for, I think there is a missing number, for an example here, like 7 is missing somehow. Or maybe 5 is missing in this particular case. We don't have the 5. We have 6, 7, 8, 9, 10, 11, 12, and 13. So I'm looking for 5. It should be in between 4 to 7, right? Now, it should be in between 4 to 7. So, for example, like this part, the left pointer is 3, right pointer is 5. And what is the midpoint? Midpoint is 4. We will check the 4 value, 4th index value with the target value 5. 6 is greater than 5. That means it should be in this particular area, 4 to 6. We can only worry about 4 to 6, not 6 to 7. That means we need to move the right pointer to mid. So now the right pointer is 4. So 4 plus 3 divided by 2 is what? 3, right? Then the 3 value, what is the 3 value? 3 value is 4, and our target value is 5. That means we need to do what? We need to move our left pointer to right and right pointer to left, right? So left pointer is here, right pointer is there. We just swap the left and right pointer. In that particular case, we cannot find it. That means as long as left pointer is less than right pointer or equal at least, we can iterate. At any point, if the left pointer is greater than right pointer, we can exit the loop or exit the iteration because we don't find it. For this particular case, 5 is not here. It just changed the left and right pointer. Does that make sense? Okay. So what is the binary search? Binary search is more efficient searching algorithm that works on sorted list only. This is the important thing, sorted list only. Instead of checking every element, binary search repeatedly divides the list into halves. And how it works, start the middle element of the list. If the middle element equal to the target, search is complete. If the target is smaller, search the left hub. If the target is larger than the mid position, search the right hub. Repeat until the element is found or the list becomes empty. That means empty means like we're done with this list. So for example, this one, 5, 10, 15, 20, 25, 30. Middle position is 15. So 0, 1, 2, 3, 4, 5. 0 to 5 divided by 2 is 2, right? So 0, 1, 2. This is the middle point, 15. We're looking for 20. So 20 is greater than 15. We need to search on the right half. So now we need to search on this part, 15 to 30. What is our left pointer? 0, 1, 2. 2 is the left pointer. Right pointer is what? 2, 3, 4, 5. 5 plus 2, 7 divided by 2 is 3. 3 is here. Now the mid pointer is 20. I'm sorry, 25, right? 25, we'll check if the 20 is less than 25 or not. If it is, see, it is not matched, it is less than, that's why we need to search for the left half. And then from 15, 25, and 20, the middle position is 20. It is exactly matched. We found it and we're done. Now, in the code, how we can implement the binary search? I told you about the two-pointer approach, left pointer and right pointer. Left pointer start from 0, and right pointer is like len minus 1. Since the length is 12 here, so len minus 1 is 11, 11th index. And how long I will iterate? Until the left is less than or equal to right. Then I will iterate. And then every time I will calculate the mid position. How I can calculate the mid position? By the integer division of left and right divided by 2. I will check if that particular midpoint value is exactly target. If it is, return the mid. If it is less than target, I will shift the left position to mid plus 1. Like mid is not exactly matched. So start from here, mid plus 1. Otherwise, I will shift the right position to mid minus 1. Either this part or that part, skipping the mid position. That's why mid plus 1 and mid minus 1. Okay? Does that make sense? It is one of the trivial problem in computer science, binary search. And whenever you are solving any problem in a linear way and someone asks you, can you make it better? That means definitely they're looking for a binary search. So to make sure they're sorted. If they're not sorted, this way, no, you cannot solve this because they're not sorted. I cannot make it better. Okay. So what are the characteristics and advantages? Much faster than linear search for large data, but the disadvantage is it requires a sorted list. And every time it creates the half of the list. So at the end of the time, it will reduce the space size to log of 2 of m. So for example, if it is like 100, what is the log of 2 of 100? 100 is like 2 power of 4 is what? 32. Then 65, 64, right? So 2 power of 1 is 2, 2 power of 2 is 4, 2 power of 3 is 8, 2 power of 4 is 16, 5 is 32, 6 is 64, 7 is 128, right? So the 100 is in between 64 and 128. That means it will take around 6 to 7 times. If we just create log of 2 of 6, it is 64 actually, right? So this part is like 2 of 2 is like 1. That means it is like 6, like sort of math class. But if you're doing the linear search, it will take 64 times. In a binary search, it only takes like 6 times. That's why it is log of n. And by default in computer science, log means log of 2. This is a binary. Okay. Okay. So these are the difference between those two. Data requirement, it can be sorted or unsorted, it doesn't matter, but binary search requires the sorted. Method, it checks element 1 at a time, but it divides the list repeatedly to half. Speed, it is slower for large data set, but it is much faster for large data set, but make sure they are sorted. If they are not sorted, you cannot apply the binary search to any data set. That's why I told you order of n time, since it is linear, 1 item at a time. For this case, it is log of n. Okay. Any question about the searching? Linear search and binary search. Do you understand completely the binary search? Can I give you a problem? Different problem related to binary search? Okay. One of the trivial problem called like bad version. So here's the problem like bad version, first bad version. Whenever you are developing a software, if one version is a bad, next onward versions are always bad, right? You are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality check. Since each version is developed based on the previous version, all the versions after a bad version are also bad, right? If you have any bug in any version and you are not solving it, the recurrent versions are always the like a faulty one. So suppose you have n version, the versions are starting from 1, 1.1, something like that. But in our case, we're just writing 1, 2, 3 on until the end. And you want to find out the first bad one, which causes all the following ones to be bad. You are given an API. Do you know the API? What does it mean by the API? Like application programmable interface. Like we always have some sort of functionality to check, like library function. For example, I think we have used to modify something, but not to check. For example, like sorting, there's a function called like sort. It will sort by itself. So for example, you are given a function called like if bad version. Whenever you are passing a version, it will return a true or false. Like Boolean, it returns either true or false, whether it's a bad version or not. As I told you, by the name, you can find is bad version. True means it is bad. If it is returning false, that means it's not a bad version. So which returns whether version is bad. Implement a function to find the first bad version. So you can call this function. They have already built that function for you, but you need to call that function to check whether that particular version is bad or not. So you should minimize the number of calls to the API. So here's the input. Input is n, bad version is 4. You need to find out what is the bad version. So you're only given the n from 1 to n, and this is like the fourth one. Fourth one, you find the bad, but you're not sure whether the fourth one is the original bad one. Maybe the third one, maybe the second one, maybe the first one. You never know. You need to call this one, and if there is better, like the oldest bad version, you need to return that particular bad version. So in this particular case, whenever you call the bad version 3, it returns false. That means it is not bad version. Whenever you call 5, it returns true. It is bad version. That means 3 and 5, in between 3 and 5, 4 is the middle one, right? That means definitely fourth one is the bad version. So if it's the fourth is the bad version and you are finding the bad version of the fourth one, that means you have the bad version on the latest one. That means the previous one is not a bad one. Does that make sense? How can I solve this problem? So you have an n number. You have n number, like for example, 5. You're working on 5. You have like 5 versions. You're finding bad version on 4. How do you know that the fourth one is the first bad version, or the third one, or the second one, or the first one? So what you can do, you can just create a version listing 1, 2, 3, 4, 5, right? These are the versions. Now, you know that fourth one is definitely a bad version. You need to find out whether fourth one is the very first one, or third one, second one, or fourth one. That means we have a list of bad version, tentative list of bad version here. Fourth one is definitely a bad version, but I'm not sure whether the first one is the bad version or not. And we have a function API like is bad version. If you call this function to the number, it will return true or false. That means if you pass it to, it will return either true or false. So if it is a true, that means this is a bad version. Now, 2 is a bad version, 4 is a bad version. That means all 3 are bad version. We don't need to worry about the 3, right? 2 is bad version, 4 is a bad version, 3 is always a bad version. Then we'll check for 1 and 2. We have 1 and 2. I know 2 is a bad version. Now check with 1. So 1, is it a bad version? Maybe no. So we have only 2 items. So the 2 is the first bad version then. Does that make sense? How do you solve this problem?